let's get started. So I just wanted to say one more word about what we did at the last time, because I felt like there was a idea that was just totally left hanging, unusable. So as I explained, the basic choices that you make to define the standard model of particle physics, you choose the gauge group, but you choose Lorentz invariance or Poincare invariance, Lorentz invariance and translation invariance for the theory. And then also internal symmetries. In particular, you choose three gauge groups, SU3 times SU2 times U1. Then you're not done choosing yet. You still have to choose the representations for all of the fermions and for all of the scalar fields. And you have to choose what fermions and scalar fields are in the theory and what representations they lie in with respect to these gauge groups. What are their charges or representations? That's what that table summarizes. And now the exercise is to convince yourself that if you just try to if you think of each of these, if you think of each of these guys in the normal way as giving rise to a charge, so and you try to write down all the terms that are invariant under this hypercharge, which is just exactly analogous to electric charge, and then furthermore is invariant under these groups, meaning that it has every time there's a value that's not equal to 1. Here, this field carries an index which ranges over those values and transforms as the two-dimensional representation of SU2 or the three-dimensional representation of SU3. And the exercise is to convince yourself that if you just try to contract up all of those indices, and you restrict yourself to only write down terms such that when you add up the mass dimension of all the fields plus derivatives in the term. So every time you have a derivative in the term, you count that as having mass dimension 1, because we're working here in units where h bar is equal to c is equal to 1, where mass is equal to 1 over length. So a derivative has units of 1 over length, which is mass. Every time you have a scalar field, it has mass dimensions. Every time you have, since our scalar field is h, it has mass dimensions 1. Every time you have a fermion, it has mass dimensions 3/2. And every time you have a gauge boson, its mass dimension is 1. You go through there and write down all the terms you can think of that have all the indices contracted up, and also such that the total mass dimension in each term is not more than 4, because those are the terms that would be contained if the theory is to be renormalizable. This is what you get. And so in other words, what have I done here? Well, I've just written down, yesterday as we were deriving what is the action for Einstein gravity, we derived in parallel what is the kinetic term for a Yang-Mills gauge field. We found that it was basically you took two copies of the field strength, the analog of the curvature, the curvature of the gauge connection. You contracted up its Lorentz indices, and then you contracted up its gauge indices, which aren't shown here. But so you contract them all up by multiplying these two matrices and then tracing over the remaining indices. So I just wrote down a kinetic term for each of the gauge bosons. Then I wrote down the only gauge invariant kinetic term I could think of. By kinetic term, I just mean any term that has a derivative in it. So if I ever take a derivative of the field, I call that a kinetic term. So this is the only derivative. This is the only term involving derivatives that I can write down that has no free indices of any sort, and is so that's the kinetic term for the scalar field. Here are the kinetic terms for the fermion fields. It's just like you probably learned in your quantum field theory class that, roughly speaking, the kinetic term for a fermion field looks like this. That's the Lorentz invariant guy, where this is the so this guy would be gamma mu contracted with the Dirac gamma matrices contracted with partial mu. This is just a covariant version of that. So, for example, if this guy, what exactly the covariant version is depends on what charges this field carries. But for example, if this field carried nothing but a U1 charge and its charge was 3, the covariant derivative would be partial derivative plus I times the U1 coupling constant times 3, because the charge is 3, and then times the associated gauge coupling, for example. So depending on what the field's charges are and representations according to this table, you have to add. You may or may here you'd have to add an SU3 gauge field to the covariant derivative to make it covariant. Here you would not. Here you'd have to add an SU2 gauge field. Here you would not. So every time D appears here, it's a slightly different D that's appropriate to whatever field it's acting on. But so anyway, you have a kinetic term for basically all 6 fermions in the table here. And again, part of the exercise would be to convince yourself that you can't write down any other kinetic terms. For example, you know, U right bar D slash D right would be perfectly Lorentz invariant, but wouldn't be gauge invariant. It wouldn't have vanishing U1 charge as a whole, because this guy would have U1 charge minus 1/3. This guy, when it's unbarred, it has charge plus 2/3. So it has, when it's barred, it has charge minus 2/3. And so minus 2/3 minus 1/3 is minus 1, not 0. So it doesn't have this term as a whole. Is not invariant under U1 there, for example. So anyway, so the idea is to go through and convince yourself that these are really all the derivative interactions you can write down. And then once you've finished writing down the kinetic terms, you can ask, okay, now what remaining terms can I write down that don't have any derivatives, just purely potential terms? And there's only a few. You can write down these 2 terms involving just the scalar field. So this is another. These are its potential, and so this is the term that makes its potential look like this, and this is the term that makes its potential come back up and look like this. So that's the Higgs. Those 2 terms are the Higgs potential, and then there are just this line of terms. These are the so-called Yukawa couplings. So in other words, Yukawa couplings are just any term that involves 2 fermions in a scalar field. So I've written, again, every term that's possible that's invariant under those charges and involves 2 fermions in a scalar field here. So you see there's basically, neglecting this one for a second, there's 4 of them, and they all have basically the same form. They all take a left-handed, so the left-handed quark gets contracted with one of the right-handed quarks here, the up quark, and in this term it gets contracted with the other right-handed quark, the down quark. Whereas the next 2 terms are the analogous leptonic things. The left-handed lepton gets contracted with the right-handed lepton here, and with the left-handed lepton gets contracted with the right-handed neutrino here, and with the right-handed electron here. And in each case, I have to include an H to get the charges right, make the term invariant. And then there's one more possibility in the standard model, if you include in the standard model right-handed neutrinos, which I do because it's no longer possible to write down a renormalizable theory that fits the data without doing that. So there's one more term that you can write down, which is just a pure mass term connecting the right-handed neutrino to nu sub c. And here there's 2 bits of funny business that'll be helpful if you try this exercise. One is that, for any field, its antifield is defined as follows. It's I gamma 2 times the complex conjugate of that field. In other words, this is what I have to do if I want to complex conjugate a fermionic field, a Dirac field, and still have it transform like it used to under Lorentz transformations. I have to multiply by this I gamma 2 guy. So anyway, so that's what nu sub c is. So it still transforms just like a normal fermion field under Lorentz transformations, but if you do this to any particular fermion field, it'll transform with all the opposite gauge charges. And then also, I've used a trick. The standard model, I should say, uses a trick about SU2, which is that the 2-dimensional representation of SU2, which is what H transforms in, is secretly the same as the 2-bar representation, which is what H star would transform in. They're the same. Here is the, and here I've applied the little change of basis necessary to see that they really are equivalent transformations. So H twiddle defined this way, in terms of H star, literally transforms exactly in the same way as H does under an SU2 transformation. So you can just think of it as a different form of H that still transforms as the 2 under SU2, but has its U1 charge reversed. Okay, so yeah, just wanted to say that in a few minutes, that it's really, I can't stress how good an exercise it is to do if you haven't done it already. Yeah.
Just two small questions. Is the reason we don't write down higher derivative terms just because the couplings would be negative mass dimension?
Yeah, that's the rules. The rule that I've been playing by here is to only write down things I would have had to pay. Any other term that you could think of here that involved more derivatives, what you'd have to you'd find out that it would have total mass dimension greater than 4.
And then also, what is the sign of m squared and lambda?
Well, they're observed to be. I've written them in such a way that I've purposely written the plus sign here, whereas in a normal Lagrangian, when you add a mass term for a scalar field, you would normally conventionally write it with a minus sign. I've done that because when you do normal free scalar field, it has a potential that looks like this. So this is the m squared direction. The actual Higgs is unstable, so it has a negative mass squared and then positive lambda to the 4th. In other words, with these sign conventions, if you put a plus here and a minus here, this m squared really is a positive, measured to be a positive value, and this lambda is measured to also be a positive value. In other words, the way I'm confusing you. If you have a scalar field, its Lagrangian looks like d mu phi squared and then minus v of phi. Because remember, if you have a normal Lagrangian for a particle, it's plus its kinetic energy. Okay. Yeah, it'll just make you'll understand this. If you've never written this down, then after you write it down, you'll understand the standard model a lot better, and you'll just be in a much better place to answer any other question or to understand more deeply the answer to any other question you want to answer about the standard model. Okay, but so that aside, this is not the standard model course, so let's proceed to the actual subject of today's lecture, which is introducing a brief introduction to the sort of 3 classes of most important metrics in physics. And then in the subsequent 2 lectures, we'll really only briefly meet the actual FRW metrics that describe our universe today. And then we'll get to know them a lot better in the remaining in the subsequent 2 lectures. But okay, so the 3 guys are the maximally symmetric metrics, the Friedman-Robertson-Walker, or Lemaitre. I think really there's a historical injustice being done apparently when I call it an FRW metric, because I think this guy Lemaitre, when I call it an FRW metric, I think Lemaitre discovered it first, maybe. What can I say though? So Lemaitre discovered it first. Let it be on record that I acknowledged him, but I've always called it an FRW metric. It's too late for me to stop. And then the black hole metrics. Okay, yeah. So we'd well, let's just dive into the first one. So these maximally symmetric spacetimes are, in some sense, the most ideal spacetimes. They really turn up all over the place in physics. So we'll discuss a little bit more after we begin enumerating them. But what I just wanted to show you here is that there is a. So this includes Euclidean space, Minkowski space, the sphere, the n-dimensional sphere, the n-dimensional negatively curved hyperboloid, n-dimensional de Sitter space, and n-dimensional anti-de Sitter space. So yeah, I just wanted to show that there is a simple construction, single construction that constructs all of these spaces, and all of it's very simple to write down all of their metrics, and you see that they all are just related to one another by a little sign flip here and there, and the construction shows you where to make those sign flips. So let's just start to motivate the construction. Let's just start with the n-dimensional sphere. So the normal way that you learn to construct the one sphere, the circle, is you start by writing down, all of these constructions will involve getting the space by treating it as a surface embedded in a flat space of one dimension higher. Okay, so that's what you do with the circle. The circle, you start by writing down two-dimensional flat space with metric ds, with the flat metric. So dx1 squared plus dx2 squared. And then you embed in that space the surface. To get the circle of radius rho, you embed the surface rho squared is equal to x1 squared plus x2 squared. Okay, and then when you're constructing the two-sphere, again, the construction is analogous. You start by writing down a flat space of one dimension higher, a three-dimensional flat space. With the following metric. And again, you embed in it a surface to get the guy of radius rho. You embed this surface x1 squared plus x2 squared plus x3 squared. Okay, and so the n-dimensional case is just obtained by continuing that pattern. The n-dimensional sphere, we start by writing down a flat space of one dimension higher, a flat Euclidean space. Okay, so that's the metric of the embedding space. And let me just, it'll be useful to use this bit of notation. So let me use capital letter indices to run from 1 up to n plus 1. So the capital letters are the indices on the embedding space. And let me use lowercase Latin letters to run from 1 up to n. So those are going to be the coordinates. Those are going to be the indices on the actual surface, on the actual manifold, on the actual n-dimensional manifold that we're trying to build. Okay, but so again, so we started with the flat embedding space, this guy, and then we're going to embed in it the surface rho squared is equal to delta AB times XA XB. Okay, so in other words, delta AB, that's the Kronecker delta, right? Is that clear? So that's why this expression expands out to this expression that's purely diagonal terms. Okay, so let me just rewrite that guy. So fine. So now I've written the one remaining step here is that usually what you do is you want to get the actual, just, we've written down an n-dimensional surface. This equation, we have one equation in n plus 1 dimension, so we've restricted ourselves down to an n-dimensional surface in a space with this n plus 1 dimensional metric. The final thing we want to know is what is the n-dimensional metric induced on that space, right? Because if I write down a surface in an ambient space, it induces a metric on the surface, because now if I'm confined to live on the surface, and I go a little infinitesimal distance along the surface between between 2 points, A and A plus dA, then there's a natural metric induced on the surface, because I can just define that distance to be whatever the distance is in the larger embedding space. I just take whatever distance I would have calculated in the full x1, x2, x3 space, and define that distance to be the distance between those 2 points restricted to the sphere. So that's the metric we want to find. We want to find just the metric of the sphere itself. Okay, so to do that, let's just eliminate the n+1th coordinate, the sort of fictitious extra embedding coordinate. So let's write this guy as the Kronecker. Let me switch, from the n+1 dimensional variables. Let me just split this into the sum over the first n terms, which I can write this way, plus the n+1th term. Okay, so now let me just solve this equation for xn+1, because that's what I want to eliminate. Okay. And so here I have, well, let me not do that yet. So I'm just solving. So now I have an expression for xn+1. I just want to use that to eliminate this term. I want to eliminate all dependence on xn+1 from that metric up there. And then I'll have a metric that only depends on the first n coordinates. In this case, the only place where xn+1 appears is in this last term. So I want to get dxn+1. So let me just take d of both sides here. So I get 2 xn+1 times dxn+1 is equal to, that's a constant, so that d of that is 0. And then this guy is minus 2 delta AB xa dxb. Okay, so now let me just introduce 2 bits of notation that'll just make everything a lot easier. First of all, this quantity, the n-dimensional delta function, the n-dimensional Kronecker delta contracted with xa and xb, I'll call that, the first bit of notation, let me call this quantity, whenever I have that n-dimensional delta function contracted with one of my coordinates, I'll just define that to be the same coordinate with a lowered index. Okay? And then I'll just define x squared to be my notation for xa, xb, or in other words, x lower a contracted with x upper a. So if I do that, then this becomes rho squared minus x squared. And this equation becomes the right-hand side here becomes minus 2 x lower a dx upper a. Okay, so now if I just divide both sides by 2xn+1, so I just isolate dxn+1 on the right-hand side, and imagine substituting it in up here. I get, let's see. I get ds squared is I get the first n terms in the metric. The first n terms in the metric are unchanged because they didn't involve xn+1. So they're delta AB dxa dxb. And then the last term becomes xa xb dxa dxb over xn+1 squared, which is rho squared minus x squared. Okay, is it clear what I did there? I just took the dxn+1 and replaced it by, according to this equation, I pulled this n+1 over and put it in the denominator here. So I have xa dxa over xn+1, and then xn+1 is the square root of that guy. So then dxn plus 1 squared is just the square of that expression, which is this. Okay, so in other words, we have the metric on the n sphere is given by this, where GAB, just the Kronecker delta, plus a correction term, XA, XB over rho squared minus x squared. Okay, and so you can recover. It's easy to check that you recover from this. So this is written. This is the metric. This is the metric on the n sphere. No, it's only an n-dimensional metric now. It only runs over n coordinates instead of n plus 1. It's written in sort of pseudo Cartesian coordinates. It's still written in the Cartesian coordinates of the embedding space after I threw out one of those Cartesian coordinates. And so the normal thing would be to rewrite that in terms of normal spherical coordinates or polar coordinates. So, for example, for the case of the circle, where capital N was, where little n is 1, we started with this embedding space x1 and x2, and then we threw out the coordinate x2, or we eliminated the coordinate x2. So if you just take that construction and you replace, you change to ordinary polar coordinates here. So you replace x1 by rho cosine theta, and x2 by rho sine theta, and you just plug those expressions. Well, let's see if you plug those expressions into the full. So you plug these expressions for x1, x2, and the corresponding expressions for dx1. Dx1 would be minus rho sine theta d theta, because rho is a constant. That's the only term we would get. And similarly, x2 would be rho cosine theta d theta. So if you plug those expressions into here, you recover the familiar, the ordinary metric on the one sphere, on the circle. And similarly, if you did the three-dimensional construction, you had a three-dimensional embedding space, and you were going to eliminate the third coordinate. But if you just take, if you just plug into these two expressions normal spherical coordinates, so then you'll instead recover the normal expression for the metric on the two sphere. Okay, and yeah, I won't go through the algebra in class at risk of boring you, but hopefully you can see how you could check that after class if you were interested to do so. Okay, so what we've done so far is create. We've shown how to create the sphere, which is a maximally symmetric surface. Now the sphere has two things has two restrictions that we would like to get away from. First of all, it has only space-like directions. So it has n spatial directions, 0 time-like directions. The metric has all plus signs in it. And it's positively curved. It has k is equal to +1. And so we just want to generalize this construction. A very minimal generalization of this construction will let us get the maximally symmetric surfaces of arbitrary signatures, so with p plus directions, p space-like directions, and q minus directions, q time-like directions, and arbitrary spatial curvature. So we'll get the positively curved spaces, the negatively curved spaces, or the zero curvature spaces. So again, this is not just of academic interest. All of these things, we actually live in space-time, so where our early universe and late universe may very well be described to a very good approximation by de Sitter space, which is a space with 3,1 signature. I mean, it's space-time, and positive k, and then of course, because of the ADS-CFT correspondence, theoretical physics, an enormously important role there is played by anti-de Sitter space, which is a space of 3,1 signature and k equals negative curvature, k equals -1. Okay, so how do we generalize this? We just insert k basically in a couple of places. Okay, so again, we just want to write down two things. First is the metric on the n+1 dimensional embedding space that we're going to start with. And then we want to write down the equation for the surface in that space. So rho squared is equal to something. So for the embedding space, if we want at the end of the day to get a metric of signature p comma q, we're trying to construct this, the n-dimensional space that we're trying to construct has signature p comma q. Let's take the first n coordinates here to have the Minkowski metric with signature p comma q. So in other words, this is just the diagonal metric with first n pluses and then q minuses. Okay, but that's only an n-dimensional metric. The n+1th dimension will take to have a plus or a minus sign according to whether we want, at the end of the day, to construct a space with positive or negative curvature. Okay, so we'll add a term k dx to the n+1 squared. So again, this is just a flat space. This is an n+1 dimensional diagonal metric with constants along the diagonal, just some pluses or minuses. Anyway, so that's our embedding space. So let's give that guy a name. Let's call that metric, that flat embedding metric, eta, since it's in the n+1 dimensional space, eta capital A, capital B, and then we'll label it by what we want at the end of the day. We want at the end of the day to get p comma q, k. P comma q is our signature, and k is our curvature. Okay, and so now then the equation that we write here, the embedding equation, is nothing but k rho squared is equal to this metric. Is nothing. The quadratic form we write down is, here the embedding metric. So there the embedding space had metric delta AB. And so the quadratic form that we wrote down, rho squared is equal to some quadratic form of xa and xb, use that same embedding metric, delta AB. So we'll do the same thing here. We have the n+1 dimensional space has this embedding metric. So we use the same embedding metric in our quadratic form. So now, if you just go through the exercise, now from here it's exactly the same as before. We just write this as there's the first n terms, and then plus the n+1th term. We solve for xn plus 1 and use it and the corresponding expression for d of that expression to eliminate xn plus 1 from this metric. And when you do that, it's literally exactly the same algebra as I did over there, so I won't repeat it for fear of causing a mutiny. But at the end of the day, what you get is the metric. So now the metric for the maximally symmetric space of signature p comma q and curvature k is given by this metric, the metric taken from the first n dimensions of the embedding space. And then plus a correction term. Where again I've used introduced two bits of notation analogous to those two guys to simplify life. So again, I define xa and xb with the lowered indices here to have their indices lowered by this n-dimensional flat metric. And then x squared is just xa, x lower a contracted with x upper a. Okay, so that's it. That's the metric. And you know, because these spaces have lots of symmetry, there are a lot of different coordinate systems in which they look kind of nice. And so there's for spaces like de Sitter space or anti-de Sitter space, there's no sort of unique conventional coordinate system. You'll see a lot of different coordinate systems, and that would be kind of a mess to go. But anyway, there's just a lot of different coordinate systems, unfortunately. But they're all simply related to this guy, and this guy turns out to be particularly convenient for calculating in the general case, if you want to calculate general properties of maximally symmetric spacetimes. And so in particular, on the homework, you will check a calculation in the notes, where you derive basically the key equation, the equation. So for the maximally symmetric spacetimes, there's actually one equation that's worth remembering. So you don't have to rederive it again and again for the rest of your life. Very, very powerful equation that's very, very helpful in practical terms when you're investigating, when you're dealing with maximally symmetric spacetimes. And that is this equation for the Riemann tensor with all of its indices lowered for one of these maximally symmetric spacetimes is given by this simple expression. So first you get two copies of the metric contracted the first guy has those indices, the second guy has those indices, and then minus the opposite pairing. So minus the first guy has these indices and the second guy has those indices. From there, okay, as I say, from there you can go to a lot of places. That's a very useful expression. In particular, the other thing you'll check on the homework is that from this expression, you'll see that these maximally symmetric spacetimes are a solution of Einstein's equation. So last time we found we sort of derived the action for gravity. By taking the two simplest scalars we could find and integrating them over the manifold. So that's the action for general relativity. That's the so-called Einstein-Hilbert term. That's the cosmological constant term. And then we'll add whatever matter Lagrangian we want to that. And now when we vary this action with respect to the metric, we get Einstein's equations. Okay, where these two terms come from these two terms, and then that's equal to 8 pi g Newton T mu nu, or T mu, where the stress energy tensor T mu nu comes from varying the matter Lagrangian in a way that hopefully you met in the GR course, or they're in those notes. They're in yesterday's lecture. The derivation of this from here to here is in yesterday's lecture notes. Okay, so these maximally symmetric spacetimes. So now that you have this simple expression for the Riemann tensor, it's easy to get a corresponding, even simpler expression for the Ricci tensor, and an even simpler expression for the Ricci scalar. And then the Einstein tensor is nothing but the Ricci tensor minus 1/2 the metric times the Ricci scalar. Okay, so you get some simple expression for that, and you see it solves this equation for T mu nu is equal to 0, and for a certain value of lambda, which I always forget exactly what it is. It's probably k times n minus 1 times n minus 2 over rho squared. Is that right? Is that right? No. It's disappointing. Okay. Anyway. So the point is, physically speaking, the ones that physically speaking, these maximally symmetric solutions are of importance because they are in some sense the vacuum solutions of Einstein's equations. The positively curved, the k equals +1 solution here is the vacuum solution of Einstein's equation. If there is a positive cosmological constant, or as we'll see in a subsequent lecture, equivalently when we discuss dark energy, equivalently a positive vacuum energy density. And similarly, the k equals -1 solutions are the vacuum solutions for negative cosmological constant or negative vacuum energy density. Let's see. Okay, yeah, I just wanted to make a little table here of what to organize these guys a little bit. So let's catalog the solutions the metrics we've just derived. So there's the k equals 0 case, k equals +1, and k equals -1. So if we take the case where p comma q is n comma 0, in other words, the purely space-like metrics, the Euclidean ones, then this is, in the flat case, that's just the n-dimensional Euclidean space. In the k equals +1 case, that's the n-dimensional sphere that we derived originally. And in the k equals -1 case, it's the n-dimensional hyperboloid. Now, if we go to the case where one of the directions is time-like, n-1 or space-like, now the flat solution is Minkowski space. The positively curved solution that's de Sitter space, and the negatively curved solution that's what is meant by anti-de Sitter space. And then usually that's the end of the table. Usually we don't go to spaces with two time-like directions. And there's a pretty good reason for that. So if you have a space with two time-like, like suppose these are both time-like directions, normally you're familiar with a space with one time-like direction, and the rest of the directions are space-like. And then the rule is that physical observers can only follow time-like geodesics. So their geodesic can go up like this, but it can never bend over so far that it's traveling more in the space-like direction than in the time-like direction. And so in particular, it can't do something like this. Can't form a closed loop and come back to the same point in time. But if you had two time directions, then any direction you went would be time-like. So there's nothing to stop you going like this. That would be a physically allowed world line. And, that's a problem because this could be, you as a baby. Let me draw you as a baby here. It's kind of like a big tummy. Anyway, little arms and legs. And then here is sort of the adult you. Anyway, you get the picture. It would just be, doesn't look right. Doesn't. You going back and visiting baby you. It would be very paradoxical. So usually we cut the table off at this point, and that, for most purposes, is the catalog of the maximally symmetric spacetimes you'll actually need to know. Maybe one last thing. Maybe before we leave these guys, let me just draw a. Yikes! Okay. Geez, I got too excited about the maximally symmetric spacetimes. Okay. I'm still going to draw a picture. Okay, so we've already, you already, of course, know intuitively what this guy and this guy look like, and this guy. So let's just quickly draw a picture of these three guys. So let's say, notice that both in our construction, both this guy and this guy, the higher dimensional embedding space has one time-like direction. So it's really Minkowski space. So there are some spatial directions, and then there's a time-like direction. And so in particular, there is a light cone. Oh, wait, I started late because of Davide. So I'm not quite as behind as I thought I was. Ah, that's good. Okay, so there's the light cone in the embedding space. Oh, now this is a perfect opportunity for colored chalk. I took my quantum field theory course from this guy, Mark Wise, who's a great teacher. But every time he got to use colored chalk, it was like the first time he had ever gotten to use it. And he would always say the same thing. He would say, "Ooh, colored chalk. I love colored chalk." Anyway, so okay, that's neither here nor there. So this guy, first of all. So if you look at the embedding equation for this guy, what did our equation look like? It looked like the embedding equation was. So see, as I say, this would be the case where eta pq there would have one time-like direction, and then the additional n+1th direction would come with a plus sign. So the total embedding space has one time-like direction, so it's just Minkowski space. And then the embedding equation, k has a plus sign here. So that in that embedding equation, you take k with a plus sign. And so this space, if you just draw that on this figure, it asymptotes to the light cone from the outside. That's not a very good asymptote. Okay, so it's the sort of so de Sitter space is the sort of hourglass figure that asymptotes to the light cone from the outside. That's and similarly, if you look through, yeah. So this embedding space is the same now, but k is equal to -1 in that embedding equation, and so you can convince yourself that the n-dimensional hyperboloid is, should have used the other color. Oh well. Asymptotes to the light cone from the inside. And I've completely screwed up with my circles. They're supposed to be inside one another, but oh well. Oh, I'll do a better job down here. Will I do a better job down here? I'll try to do a better job down here. Okay, yeah, so that's de Sitter space and the n-dimensional hyperboloid. And then the final guy we want to draw is anti-de Sitter space. So anti-de Sitter space has two time-like, the embedding space has two time-like directions. One of them coming from eta p comma q, from the fact that we're going to get one time-like direction in the final answer. One coming from the extra k equals -1, minus k equals -1 when we add the n plus 1th dimension to the embedding space. Okay, and yeah, then if you just, so the embedding space now has two time-like directions. So let's say that's one of the time-like directions, and that's another one, and that's the spatial directions. Then so now the light cone tips. Now the light cone is like this. And I've forgotten to use colored chalk again. So this is possible for anyone to see what I'm doing. And the perspective is wrong. But so you guys get the point. There's a light cone. Light cone's emanating this way, and now anti-de Sitter space looks like is this guy. Yeah, again, it asymptotes to the light cone from the outside. Okay. Okay. So that basically that's what that's all I wanted to say about the maximally symmetric spaces. Now let's move on to FRW. So physically, the Friedman-Robertson-Walker spacetimes are, the idea is that at every, that there is a way to slice up the space-time into a time direction and a space direction, such that at every moment in time, the spatial direction is just one of these maximally symmetric surfaces. So it's a purely spatial surface with maximal symmetry. So the spatial section is going to be either, and since it's our universe, it's 3 + 1 dimensional. So the spatial section is either 3-dimensional Euclidean space at every given moment in time. And in that case, so in that k equals 0 case, the universe is said to be, quote unquote, flat, which is confusing terminology because although the spatial sections are indeed flat at any given moment in time, those 3-dimensional slices are flat. They have 0 curvature in a 3-dimensional sense. The 4-dimensional space-time, as we see, when you take that slice and let it expand with time, which is what it does in cosmology, the 4-dimensional space-time is not flat, but nevertheless, that's standard terminology. Or the spatial section could be the 3-sphere in the k equals +1 case, in which case the universe is said to be closed. Or it could be the 3-hyperboloid in the k equals -1 case, in which case it is said to be open. Okay, so at each given moment in time, the spatial slices are maximally symmetric. They're one of these 3 simple geometries. But then that space expands or contracts with time in an arbitrary way. It grows or shrinks. So the metric that describes that looks like this. We take the maximally symmetric geometry. So we take one of those 3 maximally symmetric geometries we just derived. In particular, we want the 3-dimensional case, and we want, again, it to be purely spatial. So we want G30K. in our notation from before, where k again can be +1, -1, or 0. But now we want to let that metric grow or shrink with time in an arbitrary way. So we multiply it by an arbitrary so-called scale factor, cosmological scale factor, A of t. And then we give it a time-like direction. And we add time to it. Okay, so that's what the Friedman-Robertson-Walker metrics are. And again, just to emphasize a little bit more, what we mean by maximally symmetric on these three surfaces is that, if you're in this space-time and you're at some point in the space-time, and you orient yourself, let's say, so that you're facing in that direction. Observe everything, make all the observations you want, and now you imagine that instead you had been oriented in some different direction. All your observations would be unable to tell you that you were looking in this direction rather than this direction. Those two directions would appear equivalent from your perspective. So there's full rotational symmetry around each point. So it's rotationally symmetric around any particular spatial point. That's known as isotropy, or spatial isotropy. And then also, if you had moved to some other point on the sphere, here I'm drawing the case in which the universe is a 3-sphere, just because it's the case that is kind of easiest for me to draw on the board. Yeah, if you move to any other point, that's also legal. Your observations again won't be able to distinguish between you being at this point and you being at this point. So it's also it's also symmetric under spatial translations, and that's called homogeneity, or again, spatial homogeneity. Okay, yeah. So physically, those are the. So there's three different rotations. 3 different degrees of freedom in a spatial rotation. 3 different directions you can translate in space. So 3 + 3 is 6. Those are the 6 symmetries that our universe appears to have on large scales, to an extremely good approximation, and that our early universe had to a really extraordinarily good approximation. Yeah, so it has basically every symmetry you can think of at a fixed moment in time in the spatial sense, but then it has no particular symmetries that involve time or that mix time and space. So in particular, you're used to the fact in Minkowski space that you describe space-time and then some other guy goes flying by at some velocity, and his spatial coordinates and time coordinates are like this, but he thinks the metric is exactly the same as you think it is. He can't tell the difference between the space-time he lives in and there's no physical observable that can tell you if you're moving or not in Minkowski space. So that's not. So in other words, Minkowski space is boost invariant. So FRW is not boost invariant. There's some particular preferred frame in which the universe is evolving, and if you are moving with respect to that frame, you can tell. There's all sorts of observations you can do to tell that you're not in the preferred frame. Yeah, so we happen to be almost in the preferred frame, and that's something we'll understand why that is next lecture. But let's see, is there anything else I wanted? So we had this one equation you should remember forever, and are deriving as one of the homework problems on the first homework. For the Friedman equation, there are 2 equations that you should you should remember. So if we take the metric with those symmetries and we plug them into Einstein's equations, so for T mu nu, and again we'll discuss why this is later in a subsequent lecture. But for now, for T mu nu can be well approximated. The T mu nu of the universe can be well approximated on large scales by the stress energy tensor for a perfect fluid, which is diagonal and with rho in the spatial with rho in the time component and p the pressure. So this is the energy density rho and the pressure p in the three spatial components. So you calculate G mu nu, you calculate the Einstein tensor for that metric, plug it into the left-hand side of this equation, take this stress energy tensor, plug it into the right-hand side of this equation. At the end of the day, there are only two, because of the symmetry, these 10 equations reduce to only two independent equations, the two Friedmann equations. So the first Friedmann equation this guy, first Friedmann equation, is this guy. Now this guy you will, in the tutorial this afternoon, show that you can derive the same equation, okay, except for the modulo the cosmological constant term. If there was zero cosmological constant, you'll see how through a purely sort of simple Newtonian argument you could derive the same equation, and it would have a well, it'll have a nice intuitive meaning that you'll explore in the tutorial this afternoon. But so normally when I refer to the Friedmann equation or the first Friedmann equation, that's the guy that I'll mean. And then the other equation is the so-called continuity equation, which says rho dot is equal to minus 3h rho plus p. Okay, where h, the so-called Hubble rate, or the Hubble expansion rate, is defined as a dot over a. The relevant quantity that appears in both these expressions. So in other words, this is log of a dot. Oh, by the way, sorry, I've been saying dot. Did you? So a, whenever I put a dot over something, that means d dt. So a dot is shorthand for dA dt. Have people seen that notation, or have I just been confusing people for several minutes? Okay. So h is defined to be a dot over a. You sometimes hear this thing called the Hubble constant. Again, that's confusing notation because that's confusing terminology because this guy, a is a function of t, and in general, h, when you calculate a dot over a, h will also be a function of t. So it's not really a constant, although people use that language all the time. Sometimes, if they're being careful, they'll specify that what they mean by the Hubble constant is the value of h evaluated today. If there's anything that would be worth calling the Hubble constant, that would be it. But so anyway, so a is so far an arbitrary function of t. So h is some other arbitrary function of t. And physically speaking, sorry, I'll stop right now. Physically speaking, this equation says if I put more matter, more cosmological constant, or more spatial curvature into the universe, those speed up or slow down the expansion of the universe, the expansion rate of the universe, according to whether they come with a plus sign or a minus sign here. Okay, so more spatial curvature, more positive spatial curvature tends to slow down the expansion. More vacuum energy or any other energy density, any other positive energy density, speeds up the expansion. So this is how the matter affects the expansion. And then this other equation says, how does the expansion affect the matter? So this says, as the universe expands faster, it causes the energy density to dilute, the energy density rho to go down, okay, because there's a minus sign here. So if h is positive, that says A dot is positive, the universe is expanding. The spatial sections are getting stretched from moment to moment in that metric. And the faster it expands, the faster the energy density at any given point dilutes away. And exactly how fast it dilutes away for a given expansion rate depends on the so-called equation of state. You need to know the relationship between, you need to know P as a function of rho. Okay, so maybe that's what, so we'll really get into in the next two lectures the physics of how particles behave in this space-time, and then how the space-time reacts to matter. And those are the two basic things you need to know to understand. Well, those are the two basic things you need to know to understand everything else about physics in our universe. So that's what we'll do in the next two lectures.